Hello and welcome. Thank you for joining us live at NASA's Kennedy Space Center in Florida. I'm Cheryl Warner in the Office of Communications. We are here today to talk about some of the science that's launching on SpaceX's 13th Commercial Resupply Services mission to the International Space Station. Launch is targeted for December 12th at 11:46 a.m. from Space Launch Complex 40 at Cape Canaveral Air Force Station in Florida. We have a number of guests that are here today. They're going to talk about some of the 4,800 pounds of research that's headed to station, along with the rest of the cargo and hardware supplies. We'll call our guests up, and you'll have a chance to ask questions. If you're following us online, we ask that you use the hashtag AskNASA. Our first speakers today are going to give you an overview of all of this research that's launching. Our first speaker is Kurt Costello. He is the Deputy Chief Scientist at NASA's Johnson Space Center, along with Patrick O'Neill, our Marketing and Communications Director for Tesis. Before they speak, though, we're going to have a short video.
Hi, I'm Patrick O'Neill, and we're here at Made in Space, the innovative company that is responsible for having the 3D printers on board the space station. Now the startup is focused on bringing fiber optic technology to the space station. In validating this new form of technology on the ISS, it can open channels to exciting endeavors like on-orbit manufacturing in low Earth orbit. Here are some of the other major payloads launching to the ISS National Lab on this mission. A startup company, BioRacis, seeks to use the microgravity environment of the space station to improve the accuracy of wireless, medically implantable glucose biosensors for day-to-day diabetes management. Budweiser will be sending 2 separate experiments in hopes of looking at gene expression and germination within barley. Studying barley in microgravity may reveal new information on the germination process. The Houston Methodist Research Institute is partnering with pharmaceutical leader Novartis on a rodent research investigation to evaluate the efficacy of an implantable drug delivery system that could assist those with muscle atrophy on Earth. Launchpad Medical will send a synthetic bone material capable of adhering bone to metal within minutes to accelerate repair. This is an ideal environment to evaluate the healing response and development of effective treatments for patients needing bone repair. This launch brings a culmination to an incredible year of research on board the ISS National Laboratory in 2017, and we thank our partners at NASA, SpaceX, and Orbital ATK. I cannot wait to see what happens on the space station in 2018 and beyond.
And we'll now hear from Kurt.
Thanks, Cheryl. The SpaceX 13 mission is bringing 34 investigations to the space station to continue the research that we've been doing there for a number of years. The space station is a unique, one-of-a-kind laboratory that has access to some environments that you just can't get here on Earth. The first and primary of those is long-duration microgravity exposure. In microgravity or free fall as we orbit the Earth, you see a lot of physical processes seem to change. You don't have buoyancy-driven convection, and that can really help out our materials science researchers and folks like Made in Space that you'll hear from later today. You also don't have sedimentation, and a lot of our colloids researchers rely on that to be able to study self-assembly of molecules on board the space station. In microgravity, you also have changes to the way fluids move and are processed. And that affects everything on a living basis. All of us, to some extent, whether we're cells, animals, or humans, rely on water and the movement of water to keep those systems alive. That changes everything, and it adds a level of stress to our animal systems and human systems. A lot of our researchers today, you'll hear about doing research on plants and animals that involve how does that stress of spaceflight affect them. And last but not least, the space station offers an incredible view, not only of our Earth's surface, but out into space as well. 2 of our experiments flying to the space station in the external trunk of the Dragon are going to be mounted outside the Space Debris System and Tesis, the Total Solar Irradiance sensor. These systems are going to be out there doing research not only to help us protect future spacecraft and missions to low Earth orbit, examining orbital debris, but also looking at the total solar output of our sun and helping us understand where our environmental models need to be revised. So we hope you're here today to ask a lot of great questions about the science going on board, and we hope you enjoy the presentations here by our researchers who are going to talk to you, each in their own way, about how they use those unique aspects of the laboratory to better their research. Thanks.
Awesome. Well, thanks, Kurt. And it's funny. Every single time that you come to a launch, you always hear people say how excited they are to be here. And it's interesting because every time that I come here, I get more and more excited about the amount of research that's going to the space station. It's not just about the smoke and the fire. It's about what's going up inside that rocket. And this launch is truly a great encapsulation of the research capabilities that the space station brings. And so at the ISS National Lab, it's our responsibility to broker research that has the capacity to benefit life on Earth. And so on this mission, we have everything from plant biology research to general life science research, rodent research, which is going to be discussed a little bit later on. We have our friends at Made in Space who are going to be talking about how they can use the space station as a place for potential on-orbit manufacturing. It's truly, a brave new world for research, and it's truly a platform for innovation that is open for business. And I think that that's one of the other things that's a critical element about this is that it's everyone that's taking advantage of this. On this launch, we're going to have major commercial companies. We're going to have startup companies. We're going to have academic researchers. We're going to be having unique partnerships. Boeing company, for instance, is going to be talking about an association that they have with Tesis as well as the Mass Challenge Startup Accelerator a little bit later on. We're going to be talking about rodent research investigation that is in partnership with the Houston Methodist Research Institute, but also with pharmaceutical giant Novartis. So truly, again, a lot of activity is happening on the space station right now, and it's really an exciting time to be involved in space-based research. But also on this mission too, I guess one of the fun things we get to do every now and then is try to bring kind of the coolness of space to everyone. And so every year we work with one unique entity to develop a mission patch that represents all ISS National Laboratory research. This past year, we worked with Lucasfilm. And so I think we were going to tee up a video that was going to talk about that association because we have 200 of those patches that are going to be flying up and then coming back down when this mission concludes.
Growing up, I was always a huge fan of science and space, and if I wasn't in the film business designing for movies, I would hopefully be working for NASA.
There is a long, pronounced history with mission patches, both from the aviation industry as well as the aeronautics industry. Traditionally, for NASA-related patches, the astronauts themselves have been designing those patches for years. But at the ISS National Laboratory, we try to collaborate with unique partners to help develop these patches that are representative of all ISS National Lab research during a given calendar year. And who better to collaborate with than Lucasfilm?
In designing the patch, I had to bring in the best designers that I could think of, and that's Kelly and Stacy of Everly Design.
He asked us, hey, would you guys be interested in working on this project? And our eyes were just like, yes.
I actually first worked with them on early designs of the Rogue One title. It was a great opportunity for the three of us to work together again. The first step was to figure out, okay, what are the iconic moments or imagery that we want to merge with the space station?
In particular, there was this one scene on Tatooine. They have that beautiful sunset. We took elements of that and derived our colors for the final piece.
Doug's creative vision was to try to include some of the droids that have been involved in the Star Wars franchise in this mission patch.
And so the obvious choice was, okay, let's design it around the new robots like BB-8 and Chopper and K2.
And that is also very symbiotic of the ISS because the ISS is all about enhancing technology.
That captured everything about the space program for me. It talked about the future, talked about the adventure, the longing for the adventure.
Our job as graphic designers is to simplify things, and in this challenge we had to take something that is an entire Star Wars universe and then also the world and blend those two worlds together.
The final design encompassed the Millennium Falcon, the Death Star, and these droids. The droids look out into this vast space of discovery and exploration. We felt like that created a wonderment that we can relate to by looking out at the stars.
The final design of the patch, I think, is a perfect culmination of everything that we're trying to achieve.
This mission patch with Lucasfilm, it really helps to represent a banner year for Tesis and the ISS National Lab as a whole in 2017. We've already had well over 100 experiments launched to the ISS National Lab, representing a myriad of scientific disciplines, from life sciences, Earth observation, remote sensing, material sciences, physical sciences, technology development, STEM and STEAM education. The ISS National Lab is truly a platform for innovation, and to be able to have this collaboration with such a recognizable brand is going to bring that research to the forefront even more so. And if everyone's lucky and I'm feeling generous, maybe I'll give you guys some of those patches a little bit later on today. Not the flown ones. You don't get those, unfortunately. I know. I'm sorry. But no, again, as the redheaded guy that was in that video was talking about, it really has been an incredible year for research on the space station. And, to see what is building, what is transpiring from the maiden spaces of the world. It's not only just researchers that are sending investigations to the station, it's also companies that are now leveraging this unique platform to enhance their business models, because who knows what's going to happen beyond this space station. So it's trying to set the foundation for what is possible now, but what's possible for the future. So again, really happy to be here and excited for the launch.
We're glad to have you here. Thank you both for that overview. We do have time for 1 or 2 questions from the audience, so if there's anything that you would ask, please direct it to Kurt or to Patrick. Don't be shy. We've got like an hour here. Right here. Oh, we'll have a microphone come to you. Sorry, he's coming.
Hi, I was just wondering, what experiment are you guys really excited about that's going to be on the cargo?
Well, that would be like picking my favorite child, and I can't do that, right? So.
You put Patrick on the spot, but maybe if I chime in, he'll be able to pick another one, and at least that way you'll get the option to choose from 2 or see more today. But I'm really excited about the plant gravity perception experiment. This is one that's going into the EMCS, which is a European facility on board that has the capability to produce artificial gravity. So not only are we interested in plants and how they perceive gravity, but we're interested in how those plants might function differently under fractional gravity, say 1/6 gravity at the moon or 2/3 gravity at Mars. We want to know where along the gravity continuum do you see that shift in the way that plants take up nutrients and perform and behave. And so Scott Wolverton's here, I think, today to talk more about that investigation. I don't want to give too much away, but I'm really excited to see how that one plays out on board.
I guess if I were to think about one thing, and you're going to hear it from our Maiden Space folks, and I've already called them out a couple of times, but it's the idea of using the station, again, not just for research, but also the potential of on-orbit manufacturing. That is an entirely new realm that we are now going to be diving into, and, excited to kind of see how they can kind of be that test bed, so to speak, that guinea pig on station.
Great. How about one more question from the audience? In the maroon chair, please.
How many of the experiments or science projects do the astronauts on board the ISS actively participate in or conduct?
That's a great question. We have investigations going on all the time that the crew members don't interact with. We have a lot of autonomous investigations, and some of our folks today will probably be telling you how they work to automate their experiments so we can reduce the amount of time the crew has to spend. Other experiments in the pressurized section, of course, are crew tended. And roughly, I'd say it's maybe about 30% of the overall number of investigations require significant amounts of crew time. So roughly about a third of those require crew time, and the crew is very diligent about getting to know the investigation, understanding the special attention the investigators need, and even has the opportunity to talk to them from time to time during the investigation if it's required.
Excellent. Well, that's all the time we have for this brief overview from Kurt. He's going to step off stage and we're going to welcome Rebecca Regan. She's from Boeing Communications. Patrick's going to stay with us, and together they're going to tell us a little bit about Boeing's partnership with Mass Challenge and the BioRaces experiment.
So is this on? Can you guys hear me okay? All right, so Patrick's actually going to answer most of your questions, but I am here from Boeing. And at Boeing, as the prime contractor for the International Space Station, we are committed to working with NASA and with Tesis to advance promising technologies and really widen the community of researchers who can perform research on board the International Space Station. So for this mission, we are sponsoring 2 experiments from the Mass Challenge competition. The first is the Launchpad Medical. That is the bone adhesive that you heard about in the video. The second is the BioRaces experiment, which is the blood glucose monitor. So Patrick will tell you a little bit about that. So we really chose these 2 experiments from the Boeing company because of their potential to benefit life on Earth and also to enhance our chances of success as we travel to deep space.
So I'm not a scientist, but apparently I get to play one on TV every now and then. So I'm going to try to do my best to be able to talk a little bit more about the BioRaces experiment. But first and foremost, it's always exciting to be able to partner with an entity like a Boeing. I mean, Boeing is such a transformative name in the aerospace industry, and for the last 4 years, to have the opportunity to work alongside the Boeing team to help fund innovative research from startups that can leverage the space station to enhance their business models. I mean, what better way to go and collaborate than to do something like that? So we're really excited about this continued partnership that we've had and these two investigations that are going up. So as it relates, though, to this investigation, I was doing some research, and apparently by 2030, the World Health Organization says that we are expecting to have as many as 366 million people be affected by diabetes. And so that's an alarming number. And now BioRaces is a company that is looking to try to enhance day-to-day diabetes management. So they're going to be sending what they call the Gluco Wizard to the station. And the thought is, again, to try to look at trying to leverage the microgravity environment to improve the efficacy and the potency and the delivery of glucose or insulin to those that are affected by diabetes in the world around us. And so one of the reasons they'd want to do that is because in the absence of gravity, fluids are looked upon in a completely different manner. So by sending this application to station and kind of seeing how things react, let's see if I can get the actual word right, monitoring the diffusion properly of the glucose that's going to be dispensed within the Gluco Wizard, then that, again, might be able to unlock some ways to really treat those that are affected by diabetes here on Earth. So I guess, at this point in time, if anybody has any questions about the partnership with Boeing and or the investigation as a whole. Hi.
I'm interested in the Glucose Wizard, and how is that experiment going to be set up? Is it going to be a rodent experiment or human subject experiment?
So that's a good question. And actually, it jogs my memory because I forgot to mention one of the other portions of the payload. And so it's not going to be a rodent research investigation. It's actually going to be housed in a Space Tango lab. And so that's one of the cool things that's also happening with the station is that you're now seeing a variety of commercial companies that now have facilities on station that have the ability to house projects and allow researchers the opportunity to send more investigations to the station like this one. So it's going to be housed in this environment, and they will be monitoring the progress of the payload itself from this. Basically, it's going to be about a shoebox size environment.
So it's just going to be that Glucose Wizard within a box, not actually.
Correct. It's not going to be something that the astronauts themselves are going to be actively working with. It's going to be residing within this Tango Lab facility.
Other questions from the room?
Make it easy, please.
Hi. Hi. So I know you mentioned that Boeing is sponsoring some of these experiments. I know you mentioned that there are companies that have presence on the ISS now. How does this work? Who pays for that? Do the companies pay for these experiments, or have sponsors who pay for them?
So that's a great question. And at the ISS National Lab, we work with everyone from commercial companies, academic researchers, and the way that it works is that the transportation, the up mass, the down mass, the astronaut as your lab technician on station, those are things that have been assumed by the American taxpayer, by you and I. We have already made that investment. The outside cost is one where, when we were talking about a company like a Space Tango that operates a facility on station, it's not, I can't just send this microphone to the station. It has to go in flight certified hardware. So that is kind of where the outside cost kind of comes into the equation.
Next question.
How many companies do you have that you're partnered with that are actually leasing facilities on ISS?
Leasing facilities, or like that have facilities on station?
They have their suites.
Right. I believe that there's 2 right now that actually have rack space on station, but I want to say that we're well over 5 that operate commercial facilities in some capacity. So Maiden Space, who's sitting behind you, they presently they operate the 3D printer on station. So that's another example of a facility that is managed and operated by a commercial entity.
So if I was a small business and I wanted to participate, would I contact you?
I would love for you to go out there and contact me.
Okay.
Absolutely.
All right.
Any other questions in the room for Patrick or for Rebecca? I think we saw a picture there very briefly.
We did, yeah.
Did you want to talk to the photo at all?
Yeah, so I mean, I think that just gives an idea of truly how how small the Gluco Wizard is, and so again, it's using station to look at, at objects big and small to solve big problems, and that is an example of what's going to be going up.
Great. Another question in the room? Question online, please.
Yeah, so Twitter user James here is asking how many experiments have actually been done on the space station?
That's a question for Kurt, but I want to say that we have eclipsed over 2,000, correct? 2,465 and counting.
Great question. All right, with that, I think we're going to move on to our next experiment. So thank you, Patrick. Thank you, Rebecca. Next, we're going to hear from Joe Hamilton. He is going to talk to us about the space debris sensor. He's got a little bit of show and tell for us. So while he's getting situated, we're going to watch a short video about SDS. All right, Joe, over to you.
Thank you. Good afternoon. I get to start by showing off some hardware. This is, if you saw in the video, on the front layer of our space debris sensor, this is how thin the front layer is. And this represents 1/4 of the sensor. So 4 of these make up the entire detection area. And it's an impact sensor, so it has to be hit in order for us to detect the debris. And we're trying to measure small debris, things smaller than a millimeter. But the idea is that we want to not just know that we got hit, but know how fast was the object, what direction did it come from, how big was it, and if possible, not what it was made out of, but how dense is the object. Like, was it dense like steel, or was it very light like plastic, or possibly in between like aluminum? So there are 2 real objectives we're trying to accomplish here. The first is to take this combination of techniques with the 3 layers and do a flight demonstration to see how well it works, and use it in space, get the measurements, learn from it so that we can improve upon it for sensors in the future. The other main objective we have is to actually collect data. So we try to make it big enough and intend to keep it up there for at least 2 years so that we can gather statistics on the environment with the right information that's suitable for our modeling team to be able to incorporate it and improve our models.
All right. Thanks. So we'll take questions if you have them about space debris or the sensor itself.
Yes.
Please just wait for the microphone.
You were just talking about densities of various objects. I was wondering if you had yet been able to plot a graph to give you an idea of what the most numerous types of densities are that you will be occurring.
In the engineering models that have been made of the environment, we have an estimate of, in 3 different categories, high, medium, and low density. And so that's primarily what we're trying to do with this sensor, is to help us to be able to confirm and to measure at the space station altitude what the relationship is between those so that we can use that to update the models.
Of the debris that's at the altitude of the space station, how much of that is human generated and how much of it has been there just orbiting Earth?
Essentially, all of it is made by humans. The things that were natural generally come from outside of Earth's orbit, and we could get hit by that, and we're trying to be able to tell the difference between that and the things that are in Earth orbit. But essentially, everything that hits us that is from Earth orbit is we put there.
And Joe, just to clarify, you said 1 millimeter, so a paint speck? That's how small we're talking about measuring here?
We'll actually be smaller than that, even as small as a small grain of sand is the smallest that we'd be able to detect. And of course, anything larger than that that hits us, we'll know it.
In advance.
Yes.
All right, next question, please.
So along the same lines, what's the material of that outer panel made of? And like, if it gets broken, if you get hit by something bigger than a millimeter, is that why there's another one behind it? Or what happens if one of those panels is broken?
So I don't have all the design details available, but it's essentially a flexible circuit board. And the idea is that when it gets penetrated, it's going to break resistive grid lines, and the lines run horizontally across this panel. And when the line breaks, we'll be able to measure a change in the resistance that indicates that a line is broken. So when we get a hit, we'll know whether we get 0, 1, 2, or 3 lines broken, and use that to estimate the size of the object.
But if it's broken, it doesn't ruin the whole panel?
No, it doesn't ruin the whole panel. What happens is it'll damage that one place where it impacts. And then it will continue through to the second layer, and the second layer will also receive damage. But the acoustic sensors that are here, there are 4 in the corner of each one of these quadrants. And those allow us to pinpoint exactly where that damage took place and when it took place, so that we could get a velocity vector. 2 points in time and space give us a direction and speed.
We'll start up front here.
Yes, I was wondering, you said that most of the debris are man-made. Where do they come from? I mean, what is it basically?
The small pieces come from a variety of sources. There can be events when we launch and staging events, small pieces may come out. But there's also breakup events and things that happen so that when there's collisions in space, they create smaller pieces. So unfortunately, if you have a small piece and it hits a larger piece, it creates more smaller pieces. And so that's what we're trying to do, is measure and understand how that's progressing and how much of the small debris is out there that we can't track from the ground.
All the pieces result of man's activity in the space. It's not coming from Earth, and it's not plastic. I don't know how it would get in the sky, but it's linked to the space activity, to the launchings and to the rockets and.
Right. The things that hit us from Earth orbit, we expect to be from things that were man-made. And we could get hit by something that from the solar system that comes in, a micrometeoroid impacting us, and we'll try to tell the difference by understanding what direction and velocity it came from.
A couple questions in the back.
Thank you, very nice. I'm wondering, you mentioned a 2-year lifetime. What's the life limiting factor on this experiment, or could it go forever if you have the space?
Okay, well, the limiting factor will be that each time we take a hit, we get some damage on it, so that progressively with more and more damage, we'll have less full detection area to make the measurements from. But It's actually because of the large size that we have and the very small damage that these pieces make. It will depend upon the environment. If there's more hits, then it will be a shorter period of time. But we anticipate that we'll be able to keep it operational for probably close to 5 to 10 years, depending upon how long, how much damage we actually take. But the sensor, we're hoping to be up there as long as it still works and we're still collecting data from it.
Question in the back.
Thank you. How much of a threat would you say space debris is to the ISS? And is there any other big picture plan to maybe deal with the space debris beyond detection?
Okay. The first question is how much of a threat. The space station has shielding and is well shielded, and the station program monitors and decides how much risk there is and what to do about it in terms of operations for the space station. So they'd probably be better to tell you what their posture is on that, but certainly they want to understand the environment, and they do have a lot of protection from it. Your second question was?
Is there any other future plans where detection can actually be advanced? I don't know. It's kind of vague.
Okay.
For you. Yeah.
The idea for this is that we will be taking our lessons from how well this works in space, and we are hoping to put additional sensors at higher altitudes in low Earth orbit where there could be a lot of debris that we really haven't had a chance to sense yet, and include that information in the models for other spacecraft that are operating in those altitudes.
And we're going to take a question from online, please.
There's two questions here related to this. One comes from Twitter user Andrew, who asks, how many impacts is the SDS able to handle over its 2-year life?
That's something we're testing, right?
That is what we're going to test. That's really one of the things that we'll want to find out is how many can it take. And so, from an environment standpoint, we hope that we take just enough to prove that it's working well, and then no more than that. But we do expect that it should be able to detect hundreds of hits if that's what we get.
All right, and then Twitter user Eric here asks, so the sensors measure 1 millimeter, but what size can actually damage the ISS or other satellites?
Okay, something that is on the size of 1 millimeter can cause damage to things like windows, or it can create sharp edges. So, say on a handrail, an EVA glove could be damaged by grabbing a sharp edge if we didn't know it was there. Most other things depend upon the design of the system on whether they're vulnerable to it or not.
All right, I know there were other questions in the room, but we do got to move on to our next experiment. So thank you so much, Joe.
Thank you.
While he's exiting stage, we're going to welcome Candace Carlisle. She's the Tesis project manager, and Peter Blueski, he's a lead scientist from the University of Colorado Boulder. And Tesis, I'm probably going to botch this, total and solar irradiance sensor?
Yes,
close enough. There we go.
Solar irradiance
Yes.
sensor, yes.
Yes.
And we're going to start with an overview video.
Okay, thank you.
Imagine that these 100 pennies represent the total energy input from the sun to Earth. That energy fluctuates over time. For a long time, scientists have known that the sun's energy changes in a fairly regular solar cycle. The period from minimum to maximum and back to minimum is about 11 years, but even with those cycles, there's very limited variation in total energy output. These are solar energy measurements collected by a variety of missions over the years. The question, however, is precisely, how much does the sun's energy output change? Experts think the number is pretty small, perhaps just 1/10 of 1%, a tenth of a penny. But 1/10 of 1% from the sun can have a profound influence on Earth. In terms of climate change research, scientists need to understand the balance between energy coming in from the sun and energy radiating out from Earth, as modulated by Earth's surface and atmosphere. That's why NASA is launching Tesis, the Total and Spectral Solar Irradiance Sensor. An accurate solar energy measurement enables other influences on Earth's energy balance to be isolated and more accurately quantified. That will pay big dividends in terms of understanding human and natural influences on Earth's climate.
So we live on a sun-powered planet. The sun influences everything about our lives, our weather, our climate, even the ocean currents. And taking measurements from space is an ideal way to find out about things on Earth, because that lets us look at the Earth as a system. NASA has been studying the sun's energy input to Earth from space for 40 years, since 1978. And so Tesis is the latest NASA instrument to look at this measurement. ISS, roll clip here, provides an ideal location to look at Earth from space. It allows us to get up there on the launch vehicle. I was serious about the clip. Okay. It allows us to get up there on a launch vehicle and have a convenient place to hang out for a few years. And when it's on the space station, Tesis will be able to look at the sun from the perspective of the top of the atmosphere, and it operates pretty much like a sunflower. It follows the sun from sunrise to sunset, and then during the dark period, it kind of rewinds back and calibrates. Now, on space station, sunrise to sunset, that whole period of an orbit's about 93 minutes. So we see quite a number of those every day. Now, Tesis is following on to the Solar Radiation and Climate Experiment source, which launched in 2003. Tesis is going to provide the most accurate measurements to date. And in fact, for the total solar irradiance measurement, it's going to be about 3 times lower uncertainty than source was. Goddard Space Flight Center, where I'm from, provides the management of the project. And we also have the Goddard Earth Science Data and Information Services Center, which distributes the data to everyone, even you. You can go do a search and find the Tesis data about 6 months after launch when it gets online. The Laboratory for Atmospheric and Space Physics at the University of Colorado built and tested the instrument. They've been working on this a really long time. And they built the pointing platform that will help Tesis follow the sun. They're also going to do all the science operations there and the science data processing.
Thank you, Candace. I am Peter Blueski at the University of Colorado, the Laboratory for Atmospheric and Space Physics. And Tesis, or the Total and Spectral Solar Irradiance Sensor, makes 2 fundamental measurements for understanding the Earth system. And those 2 measurements are right in the name: total solar irradiance and solar spectral irradiance. Roll the first clip, please. Total solar irradiance is a measure of all of the radiant energy or light energy that Earth receives. And as Candace mentioned, this is larger than any other external source of energy to Earth and its atmosphere, and by a large amount. Like it's several thousand times greater than all of the other combined sources of energy. So it's been said, and it's very true, that trying to understand climate without measuring the sun is like trying to balance your checkbook without knowing your income. Now, does anybody balance their own checkbooks anymore? You probably allow the bank to do it, right? Would you allow the bank to do it without the bank knowing your income? No, of course not. So, same thing. The other fundamental measurement is solar spectral irradiance. This is also a measure of light energy, but broken out by individual wavelengths. Now, we're all familiar with visible light. This is light that we can see with our eyes. But there are other forms of light that we cannot sense with our eyes. That's in the ultraviolet and in the infrared. Interestingly enough, that makes up about half of the sun's energy. Only half of it is in visible wavelengths, roughly half. And why do we want to know that measurement? Well, it turns out that the components of the Earth's atmosphere interact with light of different wavelengths in very different ways. For example, ozone in the stratosphere absorbs ultraviolet radiation. You've probably heard that. You know it's very it acts as a protective shield for life on the surface. But that absorption of solar radiation in the stratosphere warms the stratosphere. It creates changes in circulation. And so it has climate impacts. It has impacts, again, on heating, but also on human health. To summarize, these two fundamental measurements, total solar irradiance essentially is a measure of all of the Earth's energy that is used to drive all processes on the planet. And solar spectral irradiance is needed to understand how the atmosphere responds to these small changes in the sun's output. Thank you.
All right, we'll take questions from the audience. So I have a couple of questions. Take my moderator privilege. Tesis is going up in the trunk of Dragon, correct? So when is it actually going to be installed on station, and what's that process entail?
They're actually looking at two different alternatives for when to install it. They don't like to do work on the station when the sun's at a high beta angle. That means that they need to put their solar arrays in a certain position and conserve their power. So they're either going to do it before Christmas or after Christmas. As of last I heard, the most likely was after Christmas, so it'll be about a couple weeks. Then they'll take it out of the trunk. It's actually the Canadian robot arm. It's way cool. So the arm has like an elbow where something can be stored. So the arm rides on a little train, goes out, gets it out of the trunk, puts it on the elbow, rides back to where it needs to be, and plugs it into something called an express logistics carrier, which is where a lot of the experiments go.
Awesome. How big is it, actually?
Peter gets to say that one because he has a good analogy.
Yeah. I'll give our program manager, Brian Boyle, the credit for this. We'd like to say it's as large as the mascot at the University of Colorado, which is a buffalo. So it's as large as a buffalo.
Good visual. All right, looks like we have a question online.
Sure. This question comes from Twitter user John, who asks, will the Tesis instrument be affected by Earth's magnetosphere as it collects data?
That's a Peter one.
No.
All right, I have a question here in the front row.
So how long will Tesis be collecting data from ISS, and how long will it be before scientists are able to use the data that you start collecting?
So our prime mission life is 5 years. We have, we're looking at an option for a 2-year extension. And the data should be available through that Goddard Earth Science Data and Information Services Center about 6 months after launch. And then it gets updated monthly. This being total irradiance from the sun, it's not something you need to see every day, but it's something you want to see over time, like that graph used to have all the trends over the years.
All right, do you have any more questions for Tesis? Yes. Okay.
I'm wondering what are the advantages and disadvantages of putting this on the ISS? And if you didn't have this ISS flight, what would be your option? Thanks.
Well, I would say the greatest advantage is that this gave us an opportunity to continue this 40-year record. This has been a mission that's been planned for a while, and this opportunity to be able to fly it on ISS, and the decision was made just a few years ago, and the plan was implemented rather quickly, and essentially this allows us to carry on this measurement, as Candace said, from the NASA SOURCE mission, which is currently flying. That mission is in its it'll be 15 years in January, 10 years past its nominal mission lifetime. So I would say that the biggest advantage was the ability to do it quickly, to implement this quickly. I would say the disadvantage is that we get some blockage from the structure itself and from the arrays. It turns out, though, that because of this mechanism which points the instruments at the sun, we are able to retain all of our fundamental science data and create this fundamental climate data record. So while ideally we would prefer not to have those structures causing partial blockage, we really don't lose any science, and we're able to do everything that we can.
So the orbit with the ISS is not a problem at all. That's what I'm kind of like getting at.
Not the orbit, certainly not. Because we're looking at the sun all of the time.
But we could do this from different places. We could do it from a polar orbiting spacecraft. We could do it from a sun-pointing, spacecraft sitting at a Lagrange point. There's a lot of places you could do it from, as long as you can get a good view of the sun. But you're trying to get that sun input at the top of Earth's atmosphere. That is the measurement.
All right, we have time for one more question from Chris in the back.
It sounds like with 5 years possibility of 2, you get either right under or just over half of a solar cycle on there. How much data do you get in terms of tracking the solar cycle of the sun? Like, would it be more beneficial to try to get an extension after that 2 years to try to get an entire solar cycle, or what's your option for that, or is that not affected by it?
So I think we probably both have things to say about this, but we talked about the continuity of the measurement that's been going on for 40 years, and we do things to try to calibrate this mission with the ones that came before. And on the folders that Ronnie gave out, you can see that it says Tesis 1, and the reason is because we're already studying what would we do for Tesis 2. But the cool thing, Peter can tell you more about, is that this will be a good chance to measure the upcoming solar minimum from space, of which they saw the last one on source.
It's an excellent question. I mean, the point is that we do have to maintain continuity of this data record. The measurements are becoming more accurate, and which means that the impact of a little break is not maybe as severe as it used to be, but really we rely on having overlap of these measurements. So it's exactly as Candace said, we have planned future missions then that will carry this on as well. The 40-year record, I think it's on the order of 13 different instruments that have made up that record. So we've relied on that continuity, and then having that allows us, because there's overlap, it allows us to put all of the measurements on a common calibration scale.
All right, we do have a few more investigations to get through, so thank you, Candace, and thank you, Peter. Next, we're going to hear from Chris Wolverton. He is a professor at Ohio Wesleyan University, and he's going to talk to us about the plant gravity perception, PGP.
Yes, thanks.
Awesome.
Thank you. I'm really excited to be here. I do just want to point out, as you take a look at our patch design there, all of these investigations, we're all just one of many, many members of a team, and my team includes individuals from the European Space Agency, from the User Support Operations Center in Norway, in Trondheim, in NASA here at Kennedy, and at Ames Research Center. So many, many wonderful, hardworking people that help to get this science up on station. And then, of course, all of the station support that we receive. I'm at Ohio Wesleyan University, and I've had the privilege of working with 12 undergraduate students over the last 3 years to prepare this for flight as well. So if I can get the next slide, I want you to think about the fact that the shape of every plant you've ever seen is the result of gravity sensing. Every plant that you've ever seen, from these coastal redwoods that you see in this image, its shoots are growing 2 football fields, 3 football fields. Its trunks are massive, and they're growing exactly, perfectly, straight up and down, away from the pull of gravity. And its branches aren't doing the same, but they're still sensing gravity. And they're positioning themselves in that gravity field exactly where they need to be to intercept light and to optimize their growth. If we could see the roots of this tree or the roots of crop plants or any other plants, they're doing exactly the same thing. They're constantly sensing gravity as their primary environmental cue that orients their growth and gives us the shape of plants that we see. How do they do that? That's at the heart of the research that we're doing on the station, taking advantage of the microgravity environment to add back small amounts of gravity to understand a little bit more about how plants detect gravity. if I can get the next slide, the best way to think about how plants sense gravity is when we're on the Earth, they're constantly receiving a constant acceleration force. And that acceleration, we call it 1g, is actually 9.8 meters per second squared. On the Earth, it's constant. We call it 1g. On the Moon, it's about 1/6 g. On Mars, it's about 1/3 of a g. We don't know how plants will respond to these variable gravity levels as we move and explore away from the Earth. And so understanding fundamentally at the kind of cellular or organ level how a plant senses, how it detects gravity. Can it sense a moon's worth of gravity and complete a life cycle, for example? If I could get the next slide. That gravity sensing mechanism, if I've got the animation of the starch statuoliths. So every plant has gravity sensing cells. And those cells, as you notice, contain dense bodies. They're packed with starch. And when that organ is displaced away from its starting position, those dense starch-filled packets, they fall to the lower wall of the cell. That's sort of what we understand now about how plants sense gravity. What we don't know is much about what happens after that. And so our question, our experiment is aimed at what's the least amount of gravity that a plant can detect and cause that kind of sedimentation or that falling of those heavy bodies in the cell. That's the primary question. What's the least amount? And the way we're getting at that is to add fractional gravity to plants as they grow and ask the plant, how about that? Can you feel that much? How about, here's a little bit more. We'll turn it up just a little more. Can you feel that? How about now? Now we're all the way back up to 1g. So we have planned a whole series of experiments at fractional gravity levels while we're visualizing the plants as they grow. We can watch them and we can see their response. If I could get the time-lapse video of plants responding to gravity. So these are example plants. These are the kinds of plants we'll be growing. They're a common plant in biological research. It's called Arabidopsis or mouse-eared cress. And this is 4 hours of growth response compressed into about 4 seconds of video. So it's sped up about 3,600 times normal. And that growth response, we all look at plants and they look like they're not doing much, right? But they're doing things just a lot more slowly than we can make out. So that's the kind of image we'll get back from the station. Those plants are growing on membranes just like what you see here. And this is a piece of flight hardware. It's no longer going to fly. That's why I'm able to hold it, walk it around, put it in my suitcase. But we're growing 120 of these at all different gravity levels on the station. And we're asking in normal plants and in plants that are actually unable to make starch, so they're missing their primary gravity sensor, how much gravity does it take to feel the gravity and to respond and give us plant shape? Of course, that influences not only our ability to explore. I can get the image of astronaut Kate Rubins working with this hardware. It's flown several times before. That influences, the answer to that question influences not only exploration missions in terms of going off Earth and supporting NASA's human exploration missions, but also plant shape here on Earth. Plant shape is critical in breeding programs to determine optimal growth for crop productivity in roots and in shoots. So lots of potential applications, both off the Earth and on the Earth.
Thank you, Chris. If you don't mind, for our viewers at home, if you just want to hold it still and look right at that camera, we'll give them a nice shot. And we'll get ready for questions from the audience if anyone has any. And the first question here.
I'm just curious how you create fractional gravity in a microgravity environment.
Yeah,
Thank you.
Great question. Do we have the image of Kate Rubins working with the hardware? So basically through a centrifugation system. So we have a cell culture chamber that has 2 rotors, centrifuge rotors, and these sort of stack, they align along the radius of the rotor at different distances. And the amount of gravity experienced by the plant varies depending on how far it is along that rotor arm. And so as those spin, they spin very slowly, and we can apply a treatment. Our lowest treatment, I think, is down to about 6/1000ths of a G. all the way up to 1G to get a good control for Earth response.
Unfortunately, we don't have that picture available, but we can make that available for our folks online if they're still looking for it. Next question in the back here.
Will there also be any investigation into gravity's effect on photosynthesis in plants?
It's a good question. I'm not aware, certainly not on this flight. I know there are some other plant experiments planned for this mission, none of which look directly at photosynthetic productivity. And I'm not aware of any that have. There have been a number of studies. Plant biology has been happening in microgravity in space all the way back from the 70s forward. And so there have been a number of studies that have grown plants seed to seed, completed entire life cycles, both by the US program and by other national programs. Russia in particular, the Soviets grew wheat several times, as did NASA. And so I don't think there's been a close investigation of kind of the subatomic process that happens during photosynthesis. But in terms of just general yield and output, things seem to work without gravity doing photosynthesis.
We have another question in the back.
Yeah, why did you decide to use this particular species of plant? I think you said it was a Arabidopsis, as opposed to any other species of plant, like a vegetable or whatever.
Sure, it's a great question. We work with Arabidopsis, as do probably 1,000 other plant biology labs. It's kind of known as the fruit fly of the plant world. So if you remember your high school biology, fruit flies are sort of a versatile organism. They're easy to grow in the lab, these plants are. Their entire genome is solved. So we have the whole genome sequence. You can go to arabidopsis.org and you can search any gene you want. You can order a mutation, a knockout in that gene, and get it in the lab and see what it does. So it's very handy genetically, all kinds of genetic tools to work with it. Plus, they're really small. And it's in the mustard family, so the seeds, I can pass this around later. You'll see they're very tiny seeds, and so we can fit a lot of them into the experimental setup.
Looks like we have a question online, please.
So Twitter user Ted here asks, would root or other low-lying vegetables respond differently?
That's a good question. Roots and shoots all respond to gravity. They just have different what we call set point angles. So for example, some roots or some stems, for example, prefer to kind of have a trailing growth habit where they kind of spread out along the ground. And those are still sensing gravity, but their set point, the angle of preference for their growth, is just non-vertical. So in most cases, those are not a matter of sensing gravity. They're much more a matter of how they respond.
Great questions. Anything else in the room? How about in the back here?
Hi, since the plants can sense gravity, is there a period of shock that it goes through during the launch and then when it's in microgravity?
That's great. So one of the fortunate things about this hardware, excuse me, is that we get to launch dormant seeds. And they can sit on station for a little while and still germinate fine when water is added. So part of the hardware design involves the injection of water, the hydration event then initiates the experiment. So in our case, no, they're not growing. They're in really suspended animation. So we don't have to deal with that. I think there are limited effects. There's probably some shock effects for those that are launching live plants. But in our case, it's not an issue.
Another question in the room, please.
Do you have any assumptions about what may happen, or have any thoughts?
Yeah, so the question was, do I have any assumptions about what might happen in terms of what the threshold is for gravity sensing? We have some excellent previous experiments in different species that have placed it somewhere in the 0.3 to 0.5 G range. That's sort of where we're expecting to see something, but because we're doing the entire continuum all the way down into the thousandths, we're also in collaboration with GeneLab bringing sample tissue back. So once these grow, they'll be frozen on orbit, brought back, and then a collaborator at Ohio University, Dr. Sarah Wyatt, will be isolating RNA from these to detect, for example, it could be that we see a growth response at 0.3 or 0.4 G, but a gene expression change may be lower than that. And so that would indicate maybe sensing is happening, but just no growth changes later.
All right, I think that's it for questions. Thank you for joining us, Chris. Next, we're going to hear from Andrew Rush. He is the president and CEO of Made in Space. Andrew's no stranger to our What's on Board show, that they've been with us a few times, and you've already heard from them about their experiment today. But tell us about fiber optics.
Great, thanks. I think we're going to start off with a brief intro video.
There's a really interesting question that we asked ourselves since we started Made in Space, which is, might there be something that you can make only in space that you could bring back to Earth and sell?
So we've built a pilot manufacturing facility that will take Z-band glass up into the International Space Station and then robotically and autonomously pull that glass into optical fiber.
The ideal fiber optic cable is one where the outer diameter does not change at all. There's no impurities inside of it, there's no crystals inside of it, and it's all the same material.
If you make Z-band glass fiber in microgravity, it is somewhere on the order of 10 to 100 times lower attenuation than today's traditional silica fiber.
We hope that we'll be offering, products that are manufactured in space within the next year or two. We would not be here today without NASA and without Tesis and without the investment and opening up of the International Space Station. So as was mentioned in that video, this is a payload that is hosted on the International Space Station National Lab, and we're very, very grateful to be chosen and be hosted by them. So what's going on here? So we are manufacturing an optical fiber, an optical glass called Z-band in the persistent microgravity environment that the International Space Station affords. Well, why are we doing this? Well, Z-band is really, really amazing. It has a transmission window that is like 3 times wider than silica glass, which is the glass that you find in sort of traditional optical fiber that underpins a lot of our long-haul telecommunications networks that we use every day. Whether you're wired into the wall or you're using a cell phone, some of the information that you're interacting with probably went through at some point some optical fiber. So having a really wide transmission window lets us actually send more signal down a single piece of fiber, which means bigger pipes, more data, and we all love more data. The other thing that is really interesting here, as you heard mentioned in the video, is that the signal loss that Z-band achieves, depending on wavelength, is 10 to 100 times better than silica's best attenuation. So that, again, is really, really important. And it's important for another reason that we all care about when we are dealing with, dealing with telecommunications, and that's latency. Basically your signal loss in your material is going to dictate how far I can send a signal before I have to reboost it. And in fiber optic telecommunications, we use these things called repeaters in order to reboost the signal periodically. These repeaters, really, really cool pieces of technology. However, they introduce latency into the system because they have to take the signal in, process it, and amplify it up and send it on again. But if I have a fiber like Z-band that has a signal transmission that's like 100 times better than silica fiber, that means I can go like up to 100 times further without a repeater, which means that I can lower the latency of those lines. So broadly, to really emphasize this, why do we care about this? Well, Z-band optical fiber, when it's manufactured in space, is able to achieve is potentially able to achieve this transmission spectrum that we're talking about. When you manufacture it on the ground, it turns out that there's these microcrystals that form in the fiber that ruin the signal transmission. That each one of these little microcrystals, at each domain, you lose like 4% of the light, and that just completely ruins your signal transmission. If you manufacture it in space, manufacture in a microgravity environment, that crystallization is suppressed and you get really amazing product, which can, revolutionize the telecommunication industry, which could provide better fiber lasers, better sensors, lots of different applications. So what we're doing here on this mission is taking the sort of 2-story tall drop tower that we use on the ground that's, human operated, and to produce fiber, and shrinking that down into, a single express rack locker, size of a microwave, and making that robotic. So the astronauts will take our payload out of Dragon, install it on station, give it power and data, and we'll do everything else. We'll start the process robotically. It'll clean the fiber up. It'll spool it up. It'll end the process. And once it's done, it won't quite ding like your microwave does, but then we'll take it out, put it back in the Dragon capsule, and ship it home to characterize that fiber and turn it over to customers, which will be a really, really exciting moment. This will be the first time that we've leveraged the space environment to manufacture a product in space that, because it was manufactured there, it's got these amazing properties that are actually useful and commercially viable, we hope, down on the ground. This is really a pilot factory for us. It's it's going to produce it's really proving out the manufacturing process, proving out the robotic capabilities, so that in future missions on the International Space Station or on other commercial platforms, we can scale this up to be able to service larger customer base. This material that I have right here in my hand is actually some fiber that we manufactured here on the ground. So this is about 200 meters of Z-bland fiber that was manufactured on our equipment during testing. And you can see it's like not much material there, but that's about 200 meters of material. The real spools we use on orbit are not 3D printed. They're going to be metal. So that's the kind of broad principle, and we're really excited about this mission and really excited about the broader program as we carry it forward. Thank you.
Questions from the room? Right here.
Oh, hi. So do you already have paying customers for the material, the fiber optic that you're going to be making up there?
So we have a really good channel partner in a company called Thor Labs, which is actually a subject matter expert in the optical glass itself, as well as a nice long list of people that we're in negotiations with.
Hi. How cost effective do you believe Z-bland is compared to other material that's already out there?
That's a great question. So Z-bland, when you manufacture on the ground, is used in kind of specialty fiber optic applications like fiber lasers and supercontinuum light sources, and it can sell, depending on the configuration, from anywhere from like $150 a meter to like $5,000 or more a meter, which are big numbers. We have done the analysis that once we have this going at scale, like on a scale that can produce a transatlantic line, we can, on a kind of per, sort of cents per kilobyte basis, actually be competitive, or in some cases, even more cost effective than silica optical fiber. Now there's a whole program to develop that to get there, but it's kind of an exciting thing to be able to say, hey, we have a pathway to produce large scale commercial quantities of material in space in a cost effective way.
A question from online, please.
Sure. Twitter user Ted asks, what is the durability of these fibers in comparison to some of the silicone we use today?
That's a really good question. So silica optical fiber, unjacketed, uncoated, is really fragile, just like Z-bland. So in the process of manufacturing any optical fiber, you manufacture the glass and then you coat it to give it physical strength. So this fiber that I'm holding here in my hand is actually really frail because it wasn't coated. But the fiber that will be produced on orbit will be coated and will have that physical strength similar to that of silica fiber.
Any more questions in the room?
How did you come up with the idea that the crystals were caused by gravity and that would be solved by microgravity?
That's a great question. So we didn't come up with the idea. We are like so space is a team sport. So we've actually looked at about 20 years of research that NASA and other agencies have performed, that we're studying Z-band optical fiber. And basically, some folks came up with a hypothesis to say, hey, we think that in microgravity you'll suppress this crystallization. There were parabolic flight experiments that were done that showed in that limited window of microgravity that you get on a parabolic flight that yes, in fact, we are suppressing crystallization. And so we're taking that research and our experience as the only company that's commercially operating manufacturing technologies on the International Space Station, and combining that and moving forward with this payload.
All right, Andrew, that's all the time we have for questions for you. Thank you for joining us. We appreciate it.
Thank you.
Next, we have our final researchers with us tonight. We have Dr. Alessandro Gattoni. He's the principal investigator for Rodent Research 6 at Houston Methodist Research Institute. And joining him, we have Dr. Yaseman Shirazi. She's the mission scientist for Rodent Research 6.
Thank you. So my name is Alessandro Gattoni. I'm a chairman and professor at the Department of Nanomedicine at the Houston Research Methodist Hospital. What we do in my department is developing implantable drug delivery system for the controlled delivery of therapeutics. For pathologies, they are chronic, so therefore requires administration of drugs for long period of time, ranging from months all the way to years. First image, please. In this image, you can see a number of different implants that we have developed over the years for a number of different type of application, therapeutic application, ranging from cancer to diabetes and to other kind of chronic pathologies. What makes these implants special is, number one, the ability of being transcutaneously refilled. So they are inserted under the skin, for example, in the inner arm, and they release the drug in a constant fashion over a period of time ranging from, again, months to years. Once the drugs is completely gone, then instead of explanting them and reimplant a new one, we can reach inside, reload the drug reservoir with more drug, and the implant is good to go for a extended period of time. The second thing that makes this implant special is the nanochannel membrane that we have developed. And the nanochannel membrane is the one that regulates the release of the drug over a period of time. Please, second image. These nanochannel membranes are microfabricated with the same type of technology that you use for make computer chips, and therefore can manufacture in large quantities in parallel with very tight accuracies in the dimension of the channels. We use channels that are very small. We're talking about 2.5 nanometers in size. For you to have an understanding of what 2.5 nanometer means, is about 20,000 times smaller than our hair, or comparable to the molecular size of a protein. So very, very tiny. Why do we need to go to that extreme in manufacturing complexity to use this type of technologies? Well, the reason is because we have realized that if we take channels that they are that small and we use them as a rate limiting membrane, we can achieve a very steady and controlled delivery of the drug outside of an implanted reservoir for a period of time. They're ranging up the way to months and years without any sort of pumping mechanism on board of our implants. So that makes a very small, very effective implantable delivery system. We are utilizing these implants for a variety of different applications, ranging from HIV pre-exposure prophylaxis in collaboration with large pharmaceutical companies such as Gilead Sciences, as well as another application ranging from diabetes, obesity, and metabolic syndrome for dosing thyromimetic molecule that would combat the disease. But in the context of the Rodent Research 6 experiment, we are using our implant for the delivery of formoterol in collaboration with Novartis, another pharmaceutical company. The idea is that formoterol will help preventing and potentially treating muscle atrophy, which of course, as you all know, is something that may occur in astronauts unless they train during their stay in microgravity. But of course, many people on Earth are affected by muscle atrophy, people that are at bed rest, people that after injuries or debilitating type of pathologies have to stay at bed rest for long period of time, prolonged periods. So therefore, we have the expectation that this implant may one day solve some of these challenges in patients down here on Earth. I have the actual implant that we are using in the context of the Rodent Research Experiment, and it's right here in my hands. You can see, you cannot see, it's too small. Well, good, let me see if we, You can see better this way. Oops, no, too small.
About the size of a Tic Tac, maybe.
That's right. Well, actually, in the picture, you see multiple of them. There are about hundreds of those. So they are very, very tiny and holds enough drugs for treating these mice that we send on the International Space Station for about 2 months. And Dr. Shirazi is going to present to you the project and experiment timeline.
Thank you. If I can get the next slides. So my name is Yasaman Shirazi. I'm the mission scientist for Rodent Research 6, which is actually the 7th mission in the order of the Rodent Research missions. We've been following the shuttle tradition of not going in order. If I can get the next picture. So why do we want to do this science in rodents? We all know that animal models are valuable translational models for the research that has been done. And next picture, please. And then rodents specifically will provide us extensive experimentation and applying techniques that we typically cannot do in humans. In addition, we all have different backgrounds genetically, lifestyle and all that, but the rodents are all similar, so we're only looking at one variable, in this case for model, as Dr. Grattoni mentioned. Next image, please. So these are basically 3 of our main hardware. On the left side, you see the rodent habitat. In the middle, you see the rodent transporter. That is the hardware that the mice are currently in. So we load the mice in the transporter about 24 hours before launch, so that was earlier this morning. And then on the right, you see the animal access unit that can be attached to either of those hardware to transfer the mice. And if I can get the next slide. So this is the rodent habitat up close. The mice, this is where the mice will reside during the mission. This has video capability, so we watch the mice daily for a couple of hours to make sure they are eating, drinking, and having a healthy stay on ISS. This also provides air circulation, filter capability, and food and water to the mice for the duration of the mission. Next image, please. And then as you can see, we're not up there to do all these experiments. Here we usually have a large group of people to do all the science experiments for us, so we have to rely on our talented crew members. So we have people on our team who train the crew, and then on the left side you see the microgravity science box, the glove box, and then on the right you can see our hardware. The access unit is attached to it, and that's how the crew members will retrieve the mice. They take them to the MSG or the glove box to do any type of procedure on them. And next image. So when we do experiments here on Earth, we have the luxury of big spaces, big labs, all kinds of equipment, microscopes and all that. But on ISS, we don't have that luxury. So this is where rodent research is very unique in the capability that we can do all the research in the glove box. Next slide, please. And this is all the space we have to work with. So this is where rodent research team comes into play to help to work with principal investigators such as Alessandro and his team and take their science from the lab bench to ISS and perform it on ISS. Also, the goal of rodent research is to maximize science return. So with each mission, we harvest thousands of samples, and then they're all archived in the life sciences library at NASA Ames. So each mission sets the foundation for many other research experiments. And then with each mission, we've developed capabilities with the procedures that we do with the hardware. And then if I can get the next slide. So for the last couple missions, we've been able to return the animals live. So what you see is the Dragon capsule that has splashed down into the ocean. The SpaceX team retrieves the capsule. We'll meet them at Long Beach Pier, and then we get the mice back, make sure they're all healthy, and then return them to the scientists so that they can continue their experimentation. And again, I just wanted to mention that rodent research team is a large multidisciplinary team. So we've got scientists, engineers, a large team of mission integration and operations, and I'm just here representing. It's a large team who's been working for a couple months now, and some of them are still at work, making sure we can turn over the hardware and the mice to SpaceX for tomorrow's launch.
All right, and with that, we'll take questions for our researchers. Right here in the front row, please.
Hey, how many mice are going to go up tomorrow?
For this mission, we are sending 40 mice, so each transporter can house 20 mice, 10 on each side. And then, as I mentioned, we have the live return capability. So of the 40 that are launched, 20 of them will come back live after 30 days, and then the rest will stay on ISS longer for up to 60 days.
Another question in the back here?
Yeah, I have two questions. The first one is, are the devices implanted here on Earth before they go up?
Yes, we've been doing that in the lab for the last few days. So the science team will load the implants with the treatment or the vehicle, and then there is a very small non-invasive surgery to put the implant under the skin for the mice.
Okay, and my second question is, someone made the comment that space is a team sport.
Exactly.
And we heard that, Boeing has a glucose monitor implant also going up in this. Are you going to collaborate in any way from what you are learning in the applications and share information between agencies?
Potential in the future. Both of these, the glucose monitoring device is a new capability, so I'm sure before we know it, there's another mission going up. There's nothing in work right now, but I'm sure all the scientists in the field will work on that.
And I wanted to add that this experiment, of course, involves a very large number of investigators, not just on the research side and on the NASA side, of course, but also with Novartis. Novartis is putting in substantial resources also for the analysis of tissues and samples, including funding. So it's really, really a broad investigation.
All right, I know we have a question online.
Twitter user Briley here is asking, how long will the mice actually stay on the ISS? What's their duration up there?
For up to 60 days for this mission, and like I said, half of them will come back after 30 days, and then the other half will stay for an entire 60 days.
Up front here?
How do the mice react to microgravity, aside from the medical experiment, I mean?
It's like anyone else who goes to microgravity, like the astronauts. It takes them a couple of days to get used to floating. But then after about 3 or 4 days, you don't even notice that they're in microgravity. They're ambulating normally, running around, eating, drinking. Yeah.
All right, that's going to be it for our presenters today. So thank you both. Appreciate it. And thank you all for joining us live today. As a reminder, please tune in for our launch coverage. Launch is targeted for December 12th at 11:46 a.m. Eastern. We're going to start our coverage on NASA television at 11:15. For more information about this mission itself, please check out www.nasa.gov/SpaceX or www.nasa.gov/station. Thank you all for joining us and have a great day.